Identifying cracks in corroding reinforced concrete using ultrasound. Reinforced concrete is a cheap and versatile material that combines the high compressive strength of concrete with the ability to resist stress provided by embedded steel bars. While reinforced concrete can be highly durable, exposure to harsh environments can reduce its lifetime. One of the main threats is the corrosion of the steel bars, which causes solid oxides to build up. As these oxides build up, they put pressure on the concrete, causing cracks to form and grow. Over time, pieces of the outer concrete layer can flake off or separate. As the steel corrodes, it no longer sticks well to the surrounding concrete, and the metal bars become thinner. If left untreated, this can weaken the structure. In building maintenance and repair, there is strong interest in non-destructive testing methods that can give an early warning when steel starts to corrode. Some traditional methods can measure the likelihood of corrosion or how serious it has become after it begins. However, these techniques cannot detect microcracks in concrete caused by steel corrosion. Miguel Ángel Climent, Jaime Ramírez, and their colleagues at the University of Alicante have demonstrated the applicability of new techniques that can detect these microcracks at an early stage using ultrasound waves. Their research provides the basis for future integration of these methods into routine inspections of reinforced concrete structures. Ultrasound testing in solid materials works by sending high-frequency sound waves into the material and then detecting the waves that come out the other side. The characteristics of the received waves offer valuable information about the material's internal structure. When ultrasound waves travel through a damaged material, such as cracked concrete, the received waves often behave in a non-linear way, meaning the shape of the wave changes in a complex, uneven pattern. Harmonic distortion means that extra sound signals appear at frequencies that are multiples of the original one that was sent in. If two different sound signals are sent in at the same time, the waves that come out can mix together and create new frequencies. These effects can be measured using non-linearity parameters, numbers that describe how much the wave has changed from its original form. Climent and Ramírez studied how ultrasound waves moved through reinforced concrete samples where the steel was corroding quickly. At the same time, the researchers regularly used microscopes to check the surface of the concrete for early signs of cracking and to track how those cracks grew over time. The study showed that tiny cracks and sudden widening of cracks were always preceded and accompanied by clear changes in the ultrasound signal patterns. This demonstrates the possibility for early detection of corrosion-induced cracking using the non-linear ultrasonic techniques. The researchers also found that liquids carrying rust into the cracks could interfere with the ultrasound signals, slightly changing the way they behave. Based on these findings, the team outlined what would be needed to use this ultrasound method in real-world inspections. Climent and Ramírez are hopeful that their approach could have widespread applications in real-world engineering, allowing inspectors to detect microcracks in reinforced concrete long before they produce any significant damage.